So this is for the class that on the 2nd of December, the Monday, we did a gizmo, which was locating images in lenses. As I seem to recall, the actual using candles didn't really work out very well. Like, realistically, nobody does like candles anymore. So the gizmo was good. So we took readings, or technically we made observations of different things over here, and we basically confirmed what we saw in our ray diagrams, which these are tables. These hypotheses are from what we obtained from our ray diagrams. Basically, you should know how to fill this table, and we confirmed the mirror formula. So we did 1 over dO plus 1 over di, and all of these answers should have been equal to 1 over f, depending on whatever you took as your f. So most people did 10 centimeters or 15 centimeters, which means this was 0.1 centimeters, or if it was 15 centimeters, it was slightly lower than that. I don't know what that is, 0.6 centimeters inverse, 0.6? I don't know. Whatever the 1 over 15 is. So I just wanted to talk quickly about these answers, so we'll just go over these quickly. What type of image does a converging lens produce? So it could produce either a real image if object is greater, I should say object distance, so let's just make it object distance. If object distance is greater than the focal length, it produces a virtual image if object distance is lesser than the focal length. Where must an object be located for a converging length to produce a real image? It has to be located beyond f, is where it has to be located. Virtual image is lesser than f, or DO, it must be located between, let's say between focal point and optical center. And why is the image virtual? So now there's different explanations for this. You can say that essentially because the light rays do not meet on the other side of the lens, so you extend them backwards to form image on the same side as object. You can explain that by saying the object is too close to the lens, so it doesn't, the converging lens doesn't converge those rays enough for them to meet really on the other side of the lens, basically, is what's going on. But basically the light rays meet on the same side, so that's why it's a virtual image. And you have to extend them backwards using dotted lines, right? So that's what makes it virtual. It's not a real image because it's not real light. You kind of like project the light backwards. Diverging lens always produces virtual images. Very easy. This is really what I wanted to talk about. So depending, as we know, we'll just fill this in first. So we know that if the distance to image is greater than 2f, I don't know why there's a distance to image here. This should really be, distance to object, I think. So if the distance to object is greater than 2f, we know we produce a diminished real image. Equal to 2f, we produce a same size real image. Between 2f and f, we produce a magnified real image. At f, no image, but we produce parallel rays of light. Between f and o, we have a magnified virtual image, right? So based on these characteristics, we're going to try and see which one would work where. So for example, a photocopier, you want your image basically to be the same size as your object. So that would go in here, photocopier. How about a hand magnifier? You want your hand magnified as the same side as where your hand is, right? So you want a virtual image, but you want a magnified image. So you want the image to be the same side as the object. So that would mean that this is where a hand magnifier is used. Projectors, again, you want a magnified image because you want to project something on a big screen, but you want a real image so that you can actually see it on the screen. You wanted to project it on the other side of the lens from the projector. So that would be over here. So this projector is a magnified real image. Camera lenses go over here because basically if you take a picture of an object, let's say you're taking a picture of a tree, and I kind of gave my best shot at a Christmas tree, and let's say you're taking a picture, this is your camera, you're kind of like absorbing all the right light rays and kind of focusing them on this like film over here. Right, so you're focusing all those light rays that you get on the film, this photographic film that takes the picture. When light kind of hits it, there's a chemical reaction that goes on. This was like the olden day cameras, and the picture is formed. And therefore you want, this photographic film is obviously small unless you want to carry a camera the size of a tree. And so you need a diminished image to form there. So that's why you need this to be true. And because this film is kind of fixed in place, you have to kind of zoom in and zoom out. You have to make sure that the image is properly focused on that little point by moving your camera lens in and out. So that's what happens when you kind of move your camera around. And at F will be the spotlight, because we need parallel rays of light, because you don't actually want light to converge. You just want parallel rays of light so that you can see clearly. And that was the uses of converging lenses, the uses of each type. And so this was an add-on to our ray diagrams, which I told you to do for homework, but now this is like you have an example for each one. So that's good, and you should do that. So I will see everybody in class. Have a good day.